So welcome to Math 310, Modern Algebra. This is Lecture 5. Today is September 16th, 2025. Anybody remember what we were doing last time? Groups, right? So what do I need for something to be a group? To be a group, what inputs do I need?
I need to be an element that's identical.
Okay, well, even before that, I need some set to discuss, right? So to be a group, need a set and a binary relation such that the following four things holds. So what was the first thing you're going to say?
There needs to be an element that's identical.
So we need an identity. So there exists an E in the group G such that for any G in G, E times G is G times E is E. So the book didn't isolate the first one as a property, but there is implicit in the definition closure. For all G1, G2 in G, G1 composed with G2, G1 times G2 is in G. So if I take two things and combine, I stay in the group. There's an identity element. What else? So you need to know these four properties. What else? Yes.
Inverse axiom?
Inverse. For all G in G, there exists an element we'll call G inverse, such that G dot G inverse is G inverse dot G is the identity, and the last is the associative. You know, for all G1, G2, G3 in G, G1 dot G2 dotted with G3 is equal to G1 dotted with G2 dot G3. Basically, I can group things any way I want, so long as I don't change the relative order of the objects. So when you're multiplying matrices A, B, C, I can first multiply A and B, and then multiply by C, or I could multiply by B and C first, and then multiply by A. And depending on what you have, certain combinations might be easier than others. So if I give you a set, all you have to do is check and see if these four properties are satisfied. And then there are some additional consequences we can have. So we talked last time. Oh, that was the review session. That's why I wasn't there. Okay. So we talked last time that we had the objects like this, and then we had a nice theorem. There's exactly one identity element, and we proved that each element has exactly one inverse, that the inverse of a product is the product of the inverses in reverse order, and the inverse of the inverses itself. So we proved the first one, and the proof is the standard prototypical type of proof you'll see in a class like this. Write down the definition and just explore the consequences of the definition, explore the consequences of what you've been given. So we talked about some examples of what is a group and what is not a group. And so if I give you a set and I give you a relation, you just have to check and see, are these properties satisfied? So the question is, how easy or hard is it going to be to check? Let's let G be real numbers X and Y such that X squared plus Y squared equals 1. Geometrically, what is that?
A circle.
It's a circle. Is G a group? Can you answer this question? So I can ask the question, is it a reasonable question? Do you have enough information to answer, is this a group? If yes, then stop proving to me that it's a group or not a group. Or if I haven't given you enough information, what information are you missing? So let's go back a slide. What do we need to have if we're going to try to understand if something is a group?
Set.
A set. Well, I gave you a set. Do we need anything else? So I've given you a set. Is this enough to determine if G is a group? Or do I need to give you something else? So can someone read the first line? What does the first line say? How bad is my handwriting?
For all G1 and G2.
Nope, that's the second line.
Oh,
First line, or the 0th line if you're a computer scientist. 0th line.
to be a group, you need a set and
A binary.
a binary relation.
Do you have enough information to answer, is G a group? No. Right? To be a group, need a set and a binary relation such that the following 4 properties hold. I've just given you a set. How do you combine 2 elements? I need a way to take pairs of numbers and combine them. So let's define x, y, and I'm going to do a cross with a circle, AB, to be XA minus, I don't know, YB, YA plus, I don't know, XB. Sure, why not? Or another way I could do it is I could do X1, Y1 combined with X2, Y2 is going to be X1, X2 minus Y1, Y2. Y1, X2 plus X1, Y2. Or another way of doing it is I could have done it as X1, X2 minus Y1, Y2, X1, Y2 plus X2, Y1. Or I could have done it as X1, X2 minus Y1, Y2, X1, Y2 plus Y1, X2. Are these all the same? Is there any difference between them? Have I defined the same operation with all of these? How do I get from the first to the second? Instead of using x, y, and AB, I'm using x1, y1, and x2, y2. Does it matter what I use to refer to a generic element? No. Which is easier for you, to use x, y, and AB, or 1s and 2s? In some sense, they're equivalent, right? But notation matters. And if you choose the right notation, it might make calculations a little bit easier. I like thinking of first element, second element. I like the 1, 2 rather than the x's and a's. The other thing is, as you start getting more and more components, eventually I'm going to run out of letters. Even if I keep using more and more alphabets, even if I go to Dr. Seuss On Beyond Z, if anybody's ever read that, where he adds more letters to the alphabet, eventually we run out. So it's nice to use indices. Now I am using, x1, y1. I could do x1, x2 for the first one and y1, y2 for the second. So that could be a third way of doing things. There's lots of different ways of doing things. What's the difference between the first blue line and the second blue line? Is there any difference going from the first line to the second line? What did I do? So are they the same or are they different? How did I get from the first blue line to the second blue line? Yeah,
The second element of that tuple is you replace the x's with y's and the y's with x's.
that's one way of looking at it. But if I do it like that, am I allowed to do that? Are the two lines equivalent?
Don't, so
So does y1 x2 plus x1 y2 equal x1 y2 plus x2 y1?
yes.
Yeah. Addition is commutative, multiplication is commutative. I can just put them in a different order. And by doing it this way, I'm starting off with the second one being defined with x1 coming first, my smallest item. And I'm basically having in each product, I'm having the x's come first. And in the last one, is that the same? Sure, I'm just flipping the order of x2 and y1 as y1, x2. And this way I'm having all of them always have my first index be first. So if you look at this now, in each expression, I always have the lower index first, the higher index second. Does anybody have any chance of believing that this is completely random? That this is just something I've just made up on the spot? Or do you think that this was carefully chosen? So can you give me numbers such that x squared plus y squared equals 1?
0 and 1.
0 and 1. Can you give me something else? Yes. 1 and 0. And so if I do that, we have to choose which one to use. Let's use the first definition over here, that we would have x1, x2, which is going to be 0, minus y1, y2, which is going to be 0, right? And then we're going to have y1, x2, which is going to be 1, plus x1, y2, which is going to be 0. And that is in G. So we just showed that if we take 0, 1 and cross it with 1, 0, we get back 0, 1. What might you conjecture if G is a group?
1, 0 is minus.
Yeah, maybe 1, 0 is an identity. Well, let's check. Let's take anything x, y that works and cross it with 1, 0. And then we would get x times 1 minus y times 0. That's just going to be x. And then we're going to get y. We're going to get ya, which is y, plus xb, which is 0. Does that prove that 1, 0 is the identity? Assuming it's a group, would this prove that 1, 0 is the identity? When we take any xy and multiply it with 1, 0, we get back xy. Does this prove that xy is the identity? Let's go back. What's our definition of the identity? E is the identity of what?
E belongs.
I'm sorry?
If E belongs in G.
So E is an element of G such that what?
EG equals to G.
Right. Oops, I type right. I wrote E here. That should be G. So it is the identity if E times G equals G times E equals G. Have we shown that here? No, we've shown only half. So we also have to look at 1, 0 cross xy. And if we do that, the first one is going to be 1 times x is x minus y. It doesn't matter. Y is 0, so we just get x. And then the second one is going to be 0 times x, which is 0, plus 1 times y, which is y. So it is an identity. So again, this tells you how careful you have to be. It wasn't enough to check that when we multiply with it on the right, that we get the identity. Yes. So if we knew that G was the group, yes. But to prove that G is a group, we have to prove that there is an identity that's a left identity and a right identity. So part of the definition of a group is there is this special element E, such that when you multiply on the left or on the right by it, you get back to where you started. So in our definition of a group, we need to prove that. If you are willing to do a couple of pages of algebra, you can actually show, I believe, if you have a left identity and left inverses, that implies you have a right identity and right inverses. You can weaken these definitions a little bit. And then if you do something like that, then you only have to prove 1/2. So a lot of times it's worth taking the hit once in your life to then have a better result in the bank. Or you just do the second calculation. Okay. Do you think that this is a good representative example to use, 0, 1, and 1, 0, in terms of what's going on? Or do you think there might be something special about these numbers? What's nice about 0, 1, and 1, 0? So when you look at these numbers, are these truly generic numbers? How did you come up with this so quickly? Who gave me the example?
In the coordinate axes?
They're the coordinate axes. You've got a 0 to make life simple. So, I'm feeling maybe it's a group, but I might be a little bit concerned because maybe the fact that we have zeros in so many places, things just work out nicely. I'd like 2 generic elements. So can somebody give me a pair of numbers whose squares add up to 1?
0.6 and 0.8.
Okay. So 0.6 is 3/5. And the other one is 4/5. Okay, can somebody give me another one?
1 over square root of 2, 1 over square root of 2.
Okay, 1 over root 2, 1 over root 2. Okay, is anybody looking forward to using the definition and multiplying everything out? No. So this is a great opportunity to talk about how can we do a calculation like this nicely. If I were to multiply x and y by 5, notice that it would multiply this expression by 5, because each expression has only one x or y, and it would multiply the second component by 5. Similarly, if I multiply AB by 5, I multiply the first expression by 5 and the second expression by 5. So I can pull out a 1/5 and a 1 over root 2 and make things a little bit nicer. This is going to be the same as 1/5 times 1 over root 2 times 3/4 cross 1, 1. Is everybody comfortable with how I did that? This is just a nice way to do the algebra. If you don't like this, keep the 5s in the denominator, keep the square root of 2's in the denominator. All right, so this is going to be 1 over 5 root 2. Then we're going to get 3 times 1 minus 4 times 1. So what's 3 times 1 minus 4 times 1? I believe that's -1. And the second is going to be 4 times 1 plus 3 times 1, which is 7. Okay. So this is the same as -1 over 5 square roots of 2, 7 over 5 square roots of 2. Is that going to satisfy the sum of its squares equals 1? So we would get 1 over 25 times 2 is 50, plus 49 over 50 equals 1. It's in G. Are you feeling a little bit more confident? Okay. Yes.
Since you, okay, so we define the group to have associated, but that's between the elements of the group, not the scalar associativity, or because you pulled out the one.
Well, what I noticed here is that if I multiply both x and y by the same number, then it multiplies the right-hand side by that same number. So I can just make my algebra a little bit simpler, and I don't have to keep the 5s in the denominators. If I didn't pull out the 5, I would just have, when I do my multiplication, I would just have a little bit more algebra. Instead of having 3 times 1 minus 4 times 1, I would have 3/5 times 1 over square root of 2 minus 4/5.
But that was only because of that relation, not because of the group itself.
Right, well, we don't know it's a group. It's only because of how I've defined my binary operation. I've defined my binary operation by saying I'm going to combine x, y, and ab as follows. And what you notice is if I just multiplied x by 2, I can't pull out a 2 because the y doesn't have a 2. But if I multiply both of them by 2, then this gets doubled, this gets doubled, this gets doubled, this gets doubled. Each piece gets doubled. So since each piece gets doubled, I can just make my algebra a little bit nicer by pulling out the 2. Okay, we need to check and see it's closed for every G1 and G2, for every pair of elements. Does anybody know how to represent an arbitrary element on a circle? How could you write an arbitrary element on a circle? So we've said that we're looking at all points that live on the unit circle. So how can you write an arbitrary point on the circle? How could you write that? Yeah. Okay, but then what dimension object is a circle? That's if you include the interior. We're only on the boundary. So what's the dimension of the boundary? That's where we live. It's 1. So because x squared plus y squared equals 1, if I give you the x, then y is either plus or minus the square root of 1 minus x squared. So I could write this point as x and then square root of 1 minus x squared if I'm taking the point up above. That's one way of writing it. There's another way of writing a point on a circle.
Cos theta.
Theta sin theta. What's the radius here? 1. So I could write this point as cosine theta sine theta. And if I give you another point, how could I write that point? I could write that point as maybe cosine phi sine phi. And now I will paste the rule again. So there's my rule. So now if I give you cosine theta sine theta times cosine phi sine phi, my rule says the first component is cosine theta cosine phi minus sine theta sine phi. And the second component is going to be YA, so it's going to be sine theta cosine phi plus cosine theta sine phi. Now it's a great opportunity to ask, what do you remember from earlier math classes? So I will ask, what do you remember from earlier math classes? Does this look familiar to you? Yes. What is the first component? Cosine theta plus phi. And what's the second component? Sine theta plus phi. And that's in G. So this shows that if I take any two elements in G, it's closed. We have now done closure. So for our example, we've got closure, we've got the identity. Now we've got to figure out, are there inverses? And then is there associativity? Associativity is basically just roll up your sleeves and do the calculation. Does anybody have a thought of what the inverse might be? When we combined two elements, it looked like we added their angles. So what might you guess? Inverse of cosine theta, sine theta. What should we try? So the way we combined them is we added the angles. And what's our identity element? Our identity element was 0, 1. Or was it 1, 0? So this is an interesting thing. Oh, it was 1, 0. Sorry, it was 1, 0. Good. So it was 1, 0. So if we want to get 1, 0, what would we need the sum of the angles to be if we want to get 1, 0?
0.
We would want the sum of the angles to be 0. And if the sum of the angles is 0, then the cosine of 0 is 1, the sine of 0 is 0. So we believe that 1, 0 is the identity. What should we take for the inverse of cosine theta, sine theta? What should we try?
90 minus cosine of 90 minus.
Well, but if we do 90 minus theta, then that's going to be cosine of 90 sine 90. That will work. I think there's something a little bit better than 90. We want the angles to give us, when we add, we want to get the cosine of 0, and we want to get the sine of 0.
Minus theta.
Minus theta, because if you tried 90 minus theta, you would get the sine of 90. What's the sine of 90? 1. And you get the cosine of 90, which is 0. So that's not quite right. So what should we try for the inverse? We want to try, cosine phi, sine phi, and we need theta plus phi to be 0, as that gives cosine of 0, sine of 0, which is 1, 0, which is our identity. So if we're trying to figure out what should we try for the inverse, we need to try to find a phi such that theta plus phi is 0. So if I give you theta, what should phi equal? Question? If there's a question, please ask me. Because if you have a question, almost surely someone else has the question.
Oh, I was just thinking about your handwriting.
Okay, no, so if you can't read my handwriting, almost surely someone else can't either. So if you can't read it, please let me know. What can't you read?
I got it now.
Okay. So that I noticed that one was bad, and that's why I rewrote the first one. So we want theta plus phi to be 0. If I give you theta, what should you take for phi?
Negative theta.
Yes, try negative theta. So try phi equals negative theta. And then we would get cosine theta sine theta times cosine negative theta sine of negative theta. Okay, in terms of even and odd, cosine is an even function. So cosine of negative theta is the same as cosine of theta. What about the sine of negative theta? How is that related to the sine of theta?
Negative sine.
Negative sine theta. Sine is an odd function. So we would get negative sine of theta. And so we're going to get cosine times cosine is cosine squared theta. Sine theta times negative sine theta is going to be minus sine squared theta. And then we're going to get sine theta times cosine theta minus cosine theta times sine theta is 0. And cosine squared minus sine squared equals
Cos 2 theta.
nope. it's cos of 0 theta, right? Cosine of theta 1 plus theta 2 is cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2. Either that or cosine squared is 1 minus sine squared. So when we put that in, this is just 1, 0. So this is either use your trig identities as, the cosine of theta 1 plus theta 2 is cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2. Or just, cosine squared is 1 minus sine squared. And so the sine squareds cancel and you just get 1. So this proves the inverses exist. So I will leave associativity to you.
And how does it cancel out?
So we have sine squared theta plus cosine squared theta equals 1. So cosine squared theta, oh wait, did I make a mistake? Sorry, is 1 minus sine squared theta. Okay, so oh sorry, this should be a plus sign here. Sorry, it's a plus sign. Yes, I typed it. That's why it wasn't canceling. I dropped a sign. And so this is the same as 1, 0. Is this a group? And again, I will leave it to you to go through and show associativity works. If I did the algebra too quickly, go through it and just do it slowly at home and convince yourself that all the algebra works, all the trig identities work. Is this a group? Yeah. Is this a strange group? Yeah. You've seen this before. This is presented in a very misleading manner. Is it reasonable to talk about points on a circle? Yes, that's reasonable. How about defining the way I combine two pairs is x, y, and ab becomes xa minus yb, ya plus xb. Does that seem reasonable? Have you seen anything like this before? You have seen it somewhere before, I believe. Do you want to be brave and guess where? So a lot of times math is hidden. And there's something fundamental, something deeper going on. So we start with the integers. What do we get after the integers? What's the next thing we move up to? Rationals. And what do we go after rationals? Reals. And what do we go after reals? Complex. Has everybody seen complex numbers? Okay, so C is the set of all z equal to x plus I, y, with x and y are real, and I is or I am the square root of -1. Okay, if I give you two complex numbers, if I give you x plus IY, and I give you a plus IB, how do you multiply those two complex numbers? We use FOIL. So it's going to be XA plus IYA plus XIB plus IYIB. Okay, that's XA. Now, what's IY times IB? What's I squared? -1. So I can just move that over here. And now the other two pieces both have an I. So let me pull out the Y and get YA plus XB. And so when I multiply two complex numbers, I get a real part and an imaginary. What I'm doing here is, here's my pair XY, here's my pair AB, and here's my new pair XA minus YB, YA plus XB. The rule is really coming from complex multiplication. Okay. If you think about these as complex numbers, some of the arguments become a lot easier. If if the absolute value of z equals 1 and the absolute value of w equals 1, then what's true about the absolute value of zw? I take a complex number of absolute value 1 and multiply by a complex number of absolute value 1. What's true about the magnitude of that number?
One.
It's also 1. And this is why it's closed. It's coming from inheriting that if I take two complex numbers of absolute value 1, their product also has absolute value 1. You could think of this as z is r e to the I theta, w is r e to the I phi. And what must the radius be in both cases? It must be 1, because I'm telling you these numbers have magnitude 1. So zw is just going to be e to the I theta plus phi. And if you look, that's essentially what we were seeing after doing a lot of algebra. This is a really good problem in highlighting that if you look at things the right way, the algebra is often a lot easier. Or that there is often a motivation behind a definition. And then the last thing is to mention, why are we doing this example today? So does anybody know what today is? Today is a very special day. It's 9/16/25, right? What's 9/16/25? What's the relation between those three numbers? Yes.
3 squared, 4 squared.
3 squared, 4 squared, 5 squared. This is Pythagorean square day. There's not going to be another Pythagorean square day for quite a while. We drop off the 2-0 from the 2025, so things work out. So if I give you a Pythagorean triple, a squared plus b squared equals c squared, we can convert this to a over c, b over c on the unit circle. What this tells us is we get something new that's on the unit circle. If you're on the unit circle, if I just multiply through by the denominator, I get another Pythagorean triple. We can use this to form new Pythagorean triples. So if I take 3/5 and 4/5 and combine it with 3/5, and 4/5, I know I can pull out 1/5 from each of them, and then I'll have 3/4 combined with 3/4. So it's 1/25. 3 times 3 is 9 minus 16. What's 9 minus 16? -7.
Yeah.
And the second component is going to be 12 plus 12 is 24. So that's going to be -7/25, 24/25. So we get a new triple. 7 squared plus 24 squared is 25 squared. We just generated a completely new Pythagorean triple just by knowing the triple 3, 4, 5. If I give you the triple 3, 4, 5, can you give me infinitely many more Pythagorean triples from that? Let's say you're back in 10th grade. How can you get a nice Pythagorean triple from 3, 4, 5? How can you get a new one? What would be a new Pythagorean triple? It can be very much related to 3, 4, 5. What's another Pythagorean triple? If you know 3, 4, 5 is a Pythagorean triple, give me another one. I'm sorry? Well, 1 squared plus 1 squared is not 1 squared.
Oh.
So you know 3 squared plus 4 squared is 5 squared. What could you do to each component to give me a new Pythagorean triple? You didn't give me 3, 4, 5 initially. What did you give me?
0.6.
You gave me 0.6, 0.8. So you gave me 6, 8, 10. How do you get 6, 8, 10 from 3, 4, 5?
Double each number.
Double each number. Can you give me another Pythagorean triple?
Triple each.
Triple each number. Can you give me another one? Quadruple. Can you give me infinitely many Pythagorean triples if you know one Pythagorean triple? Yes. Am I impressed? No. They're essentially all the same triple. Oh, wow. You multiplied each component by 2. You multiplied each component by 3. I think I know where this is going. Are you going to multiply by 4 now? Oh, you are going to multiply by 4 next. Excellent. This is one of the reasons why we, instead of looking at A, B, C, with A squared plus B squared equals C squared, we divide by C, and now we have a pair of numbers, A over C, B over C, that's on the unit circle. What we're basically saying is, I don't want you to do any stupid, tricks like this and ask for, kudos and praise for finding new stuff. You're really finding the same thing. If I double A and I double B and I double C, the ratio A over C is unchanged. The ratio B over C is unchanged. So if you try to do that trick, hey, Professor Miller, I was thinking, this is Math 310. Let's multiply everything by 310. It would give you a new triple, but it would not give you a new pair because the 310s would cancel. So if you only know 3, 4, 5, you might be hard pressed to find something that's fundamentally new and different. Some of you might know one that begins with 5. What's the one that begins with 5?
5, 12, 13.
5, 12, 13. And then I could also do 10, 24. No, we're not going to allow you to do something like that. But 5, 12, 13 would be a fundamentally new one. And then the question becomes, how do you find all of these? Well, what's interesting is this gave us a fundamentally different triple or a fundamentally different pair. And I just took 3, 4, 5, 3/5, 4/5, and I just multiplied it by itself. Instead of multiplying by itself, what if I multiplied by its flip? What if I multiplied by 4/5, 3/5? Would that be something different? Is there a way to use this kind of group connection to find all of the triples? It turns out that there's a lot of structure on the Pythagorean triples. And this is one of the great goals of group theory, is to help us try to figure out the structure of items. That there might be some hidden structure that we don't initially see. Would you think 3, 4, 5 is related to 7, 24, 25? Well, they both, the 5 and the 25 are maybe somewhat related, but this looks quite strange. And so this is a great way to try to get a sense of what's going on, is we can start playing with games like this, and then you can start asking questions. If I just keep multiplying, and now I have my new triple, and if I multiply that by 3/5, 4/5, do I get something new again? And if I keep multiplying by 3/5, 4/5, do I keep getting something new again? Do I ever return to where I started? Or do I always get something new? So there's lots of questions you can ask. There's lots of games you can play. Okay, so going back to the more formal stuff, how many of you could give me the derivative of x to the 1701 if your life depended on it with respect to x? Okay, what's the derivative of x to the 1701?
1701x to the 1700.
Perfect. Okay, you will live to differentiate again. Okay, was this hard? Okay, I want you to do it by going to the board and going from the definition of the derivative and expanding x plus h to the 1701, write down every term, subtract x to the 1701, divide by h, take the limit. Could you do this?
Not off the top of my head.
No. Could you do this?
I could.
Yes. Would it take you a while?
Yeah.
Yeah, if I had you make everything explicit and do the whole calculation out, you could do it. You might be able to argue, say, look, Professor Miller, the first term is going to be x to the 1701, the next is going to be 1701 x to the 1700h, and every term after that is going to have at least an h squared. I don't care what the coefficient, you could try to do something like that. Have you ever taken the derivative of x to the 1701 before in your life before today?
I believe so.
No, but you were able to do this immediately. How? Because you proved a rule. You proved the derivative of x to the n is n x to the n minus 1 when n is a positive integer. And because you proved that in general, if I give you something like x to the 1701, you go, oh, okay, just take n equals 1701, replace n with 1701 everywhere, and I have my result. Not hard. That's what we're doing here. We're trying to just prove a couple of results that are true for all groups so that whenever I give you a group, you can just use these results. You don't have to prove from scratch, from whatever group I give you, that this is true. So this is the advantage of doing something like this, is otherwise you would have to prove these results every single time you needed to use them. Because they hold for all groups, they're worth extracting. So we proved the first one. G has exactly one identity element. And so the proof was assume not, so then there are two identity elements, E1, E2. And then we wrote down what does that mean. So this is a proof by contradiction. Well, for E1 to be an identity element, no matter what G we take, GE1 equals E1, G equals G, and GE2 equals E2, G equals G, and then we got a contradiction. How do we get a contradiction? We chose a good value of G. When you look at this, we don't have that much that we know. We've got the elements E1 and E2. Those are the only elements we know in the group. So it's not a bad idea. Why don't we try taking G to be E1 and see what we get? Let's take G to be E2 and see what we get. So now, building on our success of proving A, what do you think we're going to do now? Proving B, right? Really not much mystery here, right? So each element has exactly one inverse. Given that the method worked well before, let's see if it works again. If it does, great. If not, try something else. So what kind of proof should we do for B? Yeah, proof of B by contradiction. So assume there exists a G with two inverses. What do you want to name them? And remember, I have bad handwriting, so what do you want to name them?
G1,
So we could name them G1, G2. Why is S a bad letter to use for a variable? It looks like 5, right? So you want to think about what's good. So what does it mean to have two inverses G1, G2? As G1 is an inverse of G, what do we have? So what must be true if G1 is an inverse of G? Equals the identity E. And as G2 is an inverse of G, we have G2G equals G2 equals E. Okay. Any questions on what we have so far? So we're just writing out what do we have, and we need to try to get to a contradiction. Okay. So how do we get a contradiction before? Well, what we did is we said, this has to hold for all G. Let's take G to be E1, let's take G to be E2, and then we got the same expression, E1, E2 equaled E2, and E1, E2 also equaled E1. So E1 had to be E2 contradiction. So what was the key insight? We had the same expression equaling two different things. Okay? And because the same expression equaled two different things, the only way that that's not a contradiction is the two different things have to be the same. So over here, we want to try to get the same expression equaling two different things. Do we have the same expression in either of these lines?
Same expression.
The same expression. Do we have something in the first that's the same as something in the second? What do we have? E. But in terms of the G1s and G2s, do we have the same thing anywhere? See, before we had E1, E2 was equal to E1, and we had E1, E2 equal to E2. We had the same expression. We had E1, E2 in two different lines. And because it was in two different lines, we said, wait a minute, E1, E2 equals E1, E1, E2 equals E2. The only way that can happen is if E1 equals E2. So the two proposed identity elements are the same. Any Red Sox fans here? Does anybody know who Big Papi is in baseball? Okay, who's Big Papi? And what's his name? David Ortiz. So if I say David Ortiz or if I say Big Papi, I'm referring to the same object. I'm just using different labels, right? I really have the same identity. I thought I might have had two identities, and I called them E1, E2, but it turns out that they're the same. There's a very famous story that when Kepler was trying to calculate the orbits of planets, he was looking at the motion of Mars, and he was hoping it was going to be an ellipse, but it wasn't an ellipse, it was a different equation. It turns out it was an alternate way of writing down the equation of an ellipse. And he didn't notice that he'd actually proven it was an ellipse. But it just looked different, and he missed for a while that, oh, no, it is an ellipse, I just wrote it in a different way. So the big insight here was we had the same expression, E1, E2, equaling two different things, so they had to be the same. So over here, I now have things involving G1, G, and G2. But I don't have the same expression on the same line. On the first, I have G1G or GG1. In the second, I have G2G or GG2. If I want to try to get the same thing, what does the first line need? And what does the second line need? What could I try to put to make them have something that's the same? So right now, the first line only involves G1 and G. The second line only involves G2G. What could I try to put in the first line and what could I try to put in the second line to get them to be the same?
G2 and G1.
Yeah, put G2 and G1. This is sort of like in linear algebra when you're trying to solve equations. If I gave you, 3x minus 4y equals 8, and maybe, 2x minus 7y equals 9. Maybe I multiply this one by 2, and I multiply this by 3 so that they cancel out. Does that look vaguely familiar? When you had systems of equations, I want to try to get things to cancel. So I multiply the top one by 2 and the bottom one by 3, and now things are going to cancel. So over here, what should I multiply both sides of this equation by? G2. Do you want to multiply by G2 on the left or on the right? If it works, you have either a 50% chance that you will choose correctly if only one works, or a 100% chance if they both work. If you try something and it doesn't work, what should you do? Try the other one. So don't think. Tell me left or right. Somebody else yell out something quickly. Left. All right, so left wins with 2 votes. All right, so multiply on left, and now we would get G2, G1G equals G2, G1 equals G times E, G2 times E. And what's G2 times E? It's just G2. And for the bottom one, do you want to multiply on the left or on the right? Do you want to do left or right for the bottom one? Let's try left. Then we would get G2, G1 equals, oh, I'm sorry, we're multiplying on the left, sorry. So if multiplying on the left, we would get G1, G2, G equals G1, G, G2 equals G1, E equals G1. Do we have the same expression? Do we have the same expression? We have G2, G1. Do we ever have another G2, G1, G? No. We have a G2, G, G1. Do we ever have that again? No. So this didn't work. So multiplying both on the left didn't work. We have to think. All right. We spend a lot of time, like 10 seconds, doing this multiplication. We'd be ashamed to throw all that work away, right? So let's just get rid of multiplying the second one on the left. What should we try now? Multiply it on the right. Let's see if that works. So multiply on right. And now we will get G2, G, G1 equals G, G2, G1 equals E, G1 equals G1. Do we now see anything that appears twice? Yes. So if you look somewhat carefully, you should see we've got a G2, G, G1, a G2, G, G1. These are the same. So G2, G, G1 equals G2 and equals G1. Therefore, G1 equals G2 and inverse is unique. And we often do a filled in square to mean QED or errata demonstratum, that which was to be proved. The proof is over now, so that if anybody is sleeping or whatnot, you can wake up and say, okay, proof is done, moving on to something new. Nice way to just break up the text in terms of what's going on. This proof, I think, is structurally similar to what we did before. I think this one is a little bit harder, but there weren't that many things to try. We don't have that many things in play. I multiplied by G1 on the bottom and G2 on the top, and I had two choices of where to put things. I could have multiplied by another element. There was one other element in play that I didn't even consider. What element did I not even consider multiplying by?
E.
Okay, sorry, two elements. There's multiplying by E, but multiplying by E is not going to help me.
G.
I could have multiplied by G, but that's not going to help me because if I multiply by G, I'm going to just keep G's and G1s up top and G's and G2s down below. So it seems to make sense that I want to try to multiply the top by a G2, and I want to try to multiply the bottom by G1. Do you think that there might be another way to prove this? Is this the only way to prove it? So could you find other expressions to look at? So I will leave you with that, is can you try to find another way to prove it? Okay. Again, to me, once you learn how to do something, this goes in your tool bag and you try to keep using it as much as possible. This is a good approach. But maybe there's another way of combining G, G1, and G2. And I will just write down, maybe looking at, G2, G, G1, that might be a good thing to look at. When I write G2, G, G1, what does that mean? How do I actually perform that? How would you compute G2, G, G1? I can only combine things in pairs. So how would I compute G2, G, G1? Is there more than one way to compute this?
Yes.
Yes. How could I compute this?
G2 bracket GG1.
So I could do as G2, then GG1, or how else could I do it? What property are we using? Associativity. Yeah, maybe that property is worth having. And so I'll leave you to try to put in the details of, can you somehow turn this into a proof? You know, if you have the divine insight, let me look at this quantity G2, GG1. And whenever I combine things, I've got to combine things in pairs. Maybe I know what GG1 is. Maybe I know what G2G is. And maybe I can then extract from this a proof. So as a good problem, you should be able to write up the details of how to use an observation like this to prove that the inverse is unique, or to prove that this method won't work. If you're having trouble doing that, please shoot me an email and let me know if you have trouble doing this. But again, I strongly urge you to try to do this. You know, this is a class where you're going to have to do some proofs. You know, giving you a bit of a hint. See if you can bring that to completion. All right, building on our success of proving A and B, what should we do next?
Proof C.
Proof C. All right. So now, C is a little bit different. It says the inverse is the product of the inverses in reverse order. So we're no longer trying to prove something like there's exactly one element with a property. We're saying the inverse of GH is H inverse G inverse. Does every element have an inverse? Yeah. So what do I have to do to show that GH inverse is H inverse G inverse? Bless you. So to prove C must show what? So what do I have to do to show that this is the inverse of G times H?
And A times H inverse times G inverse equals to the identity.
Anything else?
And H inverse G inverse times GH equals to also the identity.
So what does it mean to be an inverse? It means if I multiply on the left, I get the identity. If I multiply on the right, I get the identity. What's nice about this is I'm telling you what the inverse should be. This problem would be a lot harder if we didn't tell you what it should be, but then of course, what would be the content of C? The whole content of C is that the inverse of a product is the product of the inverses. So the idea here is that if I have the product of two elements, is there a way to figure out what the inverse of the product is by knowing the inverses of each component? So can I figure out the inverse of something complicated by knowing the inverses of each constituent part? Think of this as the Rubik's Cube. You know, if I have a bunch of moves, how do I invert? Just do the moves in reverse order. If you turn a quarter turn right, now you turn a quarter turn left. So you just invert each move one at a time and you do it in reverse order. So we just have to do algebra. So GH, H inverse, G inverse. By associativity, this is the same as G, H inverse, G inverse. We technically haven't proven that. Let's just assume this is true for a moment. If that is true, we would then get GE, G inverse, which would then be G, G inverse, which would be the identity. Okay. If I want to do things completely rigorously, does everybody know how to get to the chair's office to complain? Is there at least somebody here who can go to the chair and complain about what I'm about to do? Okay, good. So, or GH times H inverse G inverse, this is G times H inverse G inverse, right? And now I can view this as three elements. This is element 1, this is element 2, this is element 3. So this is the same as I can put parentheses like this. So here's 1, here's 2, and 3. I'm using associativity. My three elements are G, H, and H inverse G inverse. So using associativity, this is now the same as G times H inverse G inverse. Now, let's use associativity again. I can now have H inverse put together times G inverse. What's H times H inverse? So this would then become G E times G inverse. What's E times G inverse? G inverse. And what's G times G inverse? E. So if I want to do things completely rigorously and lose my job, this is how I would have to do this. What this is basically telling you is, if you have associativity, prove the following damn theorem as quickly as you can. If I have a product of a bunch of items, I can multiply them any way I want, so long as I don't change the relative ordering. So if I have 4 objects, if I want to multiply the first 2 in the middle, and then the one on the right, and then the one on the left, I can do that. If I want to multiply the first 2, and then the one on the left, and then the one on the right, I can do that. That's the kind of theorem you would want to prove. Otherwise, what I have to do very, very carefully is I've got to go through it line by line by line and justify using associativity, which only deals with multiplication of 3 items, not multiplication of 4 items. What is the derivative of a sum? The sum of the derivatives. You only prove that for the derivative of 2 functions, for the sum of 2 functions. Using that and induction, you can prove it holds for the sum of 3 functions, or 4 functions, or 5 functions. But it turns out it is not necessarily true if I give you a sum of infinitely many functions. I can give you an infinite sum of functions, and the derivative of the infinite sum is not the sum of the derivatives. But for any finite number, it works. You would want to prove a similar theorem here. If I give you any finite number of factors, I can combine them in pairs in any way I want. I can put the parentheses any way I want if it's associative, so long as I don't change the relative ordering. That's a great theorem to do. And now, for the next one, we have to do the other side. So now we would have to do H inverse G inverse times GH is similar. And so I'm not going to go through and do it. It's the same kind of calculation. So C was far more straightforward. And then the last one is prove that G inverse inverse is G. Any thoughts about how we could try to prove G inverse inverse is G? So what made C nice is I told you what the inverse of GH is. The inverse of GH is going to be H inverse G inverse, and then you just go through and show that it works. What am I telling you the inverse of G inverse G inverse is? G. What should we do? So what should we do? If we think the inverse of G is G, what should we do? To show G inverse is G, what must we show?
G inverse times G equals E.
Yeah, G inverse times G equals G times G inverse equals E. Right? But by definition, G inverse is defined so that G inverse equals G inverse G equals E. We're done. This is basically a proof by definition. What does it mean for G inverse to be the inverse of G? It means G inverse times G is G times G inverse is the identity. So if I believe that G is the inverse of the inverse, well, I just have to check, does G inverse G equal G inverse equals the identity? Yes, by the definition of what it means for G inverse to be the inverse of G. So we now have a bunch of nice properties. And so I'll do credit. So extra credit. If have a finite product in a group, prove can combine any way in pairs if do not switch ordering. So for example, x1, x2 times x3 times x4 is the same as x1, x2 times x3, x4. One way to try to prove something like this is show that no matter which grouping you have, show that it equals a specific thing, so that you get the same specific thing no matter what you start with. And then if everything is equivalent to something in common, then everybody is the same. This was similar to trying to prove everybody was named Elizabeth, right? We showed everybody was the same as person two, so therefore, since person two was named Elizabeth, everybody was Elizabeth. Except this time we're going to have a valid argument. We're going to show no matter what you give me, I can show that it's equivalent to something maybe canonical. This might be a really nice way of writing things by just having expanding parentheses as you go down. And so show that whatever I give you, you can somehow convert to being in that form. So this would be a really useful result to have. It would mean we don't have to put on all these subscripts, 1, 2, and 3, and very carefully go through things like that. Okay. So more definitions and more properties. So definition 211, the order of a group, and this notation is centuries old. This was before the era of texting, which we denote by sharp G or pound G, is the cardinality of the set of elements of G. It's just the number of elements in G. So if G is finite, it's the number of elements of G. There are other common notations that people use for the order of a group. Sometimes they use O for order. Sometimes people use the absolute value around it. And so this is just extending the notion of absolute value. You might have seen in your multivariable calculus class absolute value being applied to the length of a vector. So in your multivariable calculus class, do they do something like absolute value V? I'm old school. I like to do the double lines to just highlight the fact that I'm talking about a vector. But really, it's fine to overload the notion of what does the absolute value mean? What does that notation mean? Okay, so if the group is infinite, then we have to be a little bit careful about what do we mean by the order of an infinite group. But for a finite group, it's just count how many elements, and that's the order. So the next one, proposition 213, let G be a group, G be any element of G, and n is an integer greater than or equal to 1, such that G to the n equals E. Then the order of G divides n. So for instance, if G has order 50, so if the order of G equals 50 and G is in G, can G to the 7 equal the identity? What do you think? Is that possible? I have a group. So is it possible, can I find an element such that g to the 7th equals the e? Can anybody give me an element g that works? So I haven't given you that much. I'm just telling you, you've got some group, it has order 50. I don't even know if you know a group that has order 50. Can you find an element in that group such that if you raise it to the 7th power, you get the identity? Does anybody have a thought about what might work?
E.
E. Yes. G equals E. When in doubt, be a smartass. This helps us figure out what's a good definition. And so if I ask you, can you find an element G such as G to the 7th equals E? Yeah. Can you find an element such as G to the 1701 equals E? Yeah. This is not hard. Is anybody impressed by finding G equals E? No. Yeah, this is a trivial example. So what this means is I have to be a little bit careful with how I define things so that you can't be a smartass. So we talked about the order of a group. What is the order of an element? So he says the order of G divides N. I haven't defined the order of G. If I want this proposition to be true, I don't want there to be such an element G. Right? So what should the order be? The order of G is the smallest n such that G to the n equals E and G to the K does not equal E for any positive K greater than 0 and less than n. So it's the first time we raise G to a power and we get the identity. So when I raised G to the 7th power, if G equals E, yes, E to the 7th is the identity. E to the 6th is also the identity. E to the 5th is the identity. E to the 4th is the identity. So the smallest n I could take here would be 1. If I choose 0, we have to think about what does it mean to raise something to the 0th power. But what's 5 to the 0? 1. What's 12 to the 0? 1. So we should probably be thinking in the back of our minds, if we raise anything to the 0th power, we should be getting the identity. And so if we define the order to be the smallest positive integer, such that when we raise it by that number, we get the identity, could we still use our example of E here? We want, yeah, I mean, if we take G equals E, yes, we would get E to the 7th is equal to E, but 7 would not be the order of the element G. What would be the order of the element E? Yeah, the order of E is 1. If G does not equal E, is the order of G ever equal to 1? If G does not equal E, could G to the 1st power equal E? What do you think? G does not equal E. If the order of G is 1, that would mean G to the 1st equals E. So if I tell you G is not E, can G to the 1st equal E? No. We don't know that every element has a finite order. It could be that maybe it goes off to infinity. Maybe G, G squared, G cubed, G to the 4th, maybe it never repeats. It turns out that that's not going to happen with a finite group. Every element in a finite group is going to have a finite order, and by this proposition, that order is going to divide the order of G. Okay, so the question is, how would we try to prove something like this? What are your thoughts? Do you think the proposition is correct? Where did I get this proposition from? Did I just make this proposition up, or did you see this someplace? Where should you have seen this as you prepared for today's lecture? Textbook, right? Do you think this would be in the textbook if it's wrong? No. One would hope that a textbook like this would be carefully checked, and that if this was wrong, it would not have been published. So I'm confident that proposition 2.13 is true. I know the author quite well, very smart person, very nice person, but that's not a proof. We have to be able to give you a mathematical proof as to why is this true. And so the question is, how do we attack this? So I care more about how do we attack this than what the actual proof is. So we don't have that many examples of groups. So if you're not sure if something is true, you could gather data. We can go back, we had a list of possible groups, and we could try this, and we could see, is this true? So let's think a little bit. Consider the set E, G, G squared, G cubed, ... I'm just going to keep multiplying by powers of G. Do you think there could be infinitely many distinct elements? And it could be infinitely many distinct elements, right? But now let's assume, and we'll assume that the size of G is finite. So there are only finitely many elements in G. Is it possible to get infinitely many distinct powers of G? So let's say G has 50 elements. Could we get 75 different elements by looking at powers of G? Where do powers of G live? They live in the group G. How many elements are there in the group G? 50. Could I get 75 distinct objects in a set that only has 50? No. So eventually, I have to get the same number twice. So must eventually repeat. Right? What do you think the first element that repeats? The first time we have, let's say, G to the K equals G to the L, with K less than L. So if G to the K equals G to the L, so think if you want, say, G to the 4th equals G to the 11th. If G to the 4th equals G to the 11th, what could we do to both sides? How could we simplify things? So I've got G times G times G times G equals G times G 11 times. How could I simplify? I've got G to the 4th on the left, I've got G to the 11th on the right. G to the 7th equals 1. I could multiply both sides by G to the -4. So we get g to the minus 4, g to the 4th equals g to the minus 4, g to the 11th, or e equals g to the 7th. So if they repeat, I can look at the first time they repeat, and I can then simplify it to really, it means there's got to be some power that equals the identity. And that power can't be 1. As long as I take g to be an element other than the identity. But if I did take g to be the identity, if g equals e, what's the order of g? What's the smallest power of the identity that equals the identity? It's 1. Okay, well, 1 will divide any n. So the proposition is trivially true if we take g to be the identity. So we might as well take g to be something other than the identity. Again, right now, I don't care about the proof. I care about thinking, how would we attack something like this? How many of you have taken a proof-intensive class before? Okay. How many of you are very comfortable with advanced proofs? And so this is why I want to go slowly. I don't want to rush through the material. I want to really talk about how do we come up with stuff like this. So what we've now shown is that if I give you some element in a finite group, eventually it's got a cycle. So I would have here, say, e, g, g squared, dot, 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 g to the 6th, g to the 7th is just e, g to the 8th would be g, g to the 9th would be g squared, dot, 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 dot. So really, I would just get the powers from 1 to 7. So if I give you any element, it's going to form a set. I'm only going to have finitely many powers. So let's consider the set e, g, g squared, dot, 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 g to the n minus 1, with g to the n equals e, g to the k does not equal e if k is less than n. So I'm going to look at the elements e, g, g squared, g to the n minus 1. Is this a group? What do we have to do to show that this is a group? How many things do we have to check? 4 things. So this is a group that's living inside a group. It's called a subgroup. Yes. As lives in G, we call it a subgroup of G. And we write it as brackets G, the subgroup generated by G. So you have to show 4 things. So closure, if I give you G to the K1, G to the K2, does that equal G to the K3 with, 0 less than equal to K3 less than N? Identity. What do you think the identity is? What do you think the identity of this set E, G, G squared, G to the N minus 1? What would you guess? We don't have much time. E. It inherits the identity. Does it have inverses? Yes. Inherited. But have to show the inverses in this subgroup. So we know every element has an inverse, but that doesn't mean that it's in this set. It could be in another part of G. So we know the inverse exists. We just have to show that it lives there. And then the last is associativity. And the answer is yes. And that's, again, just inherited. So this is a good structure to possibly look at. That if I give you an element of finite order, I'm going to get a subgroup from this. And really, this is asking a more general question. If I give you a subgroup, what must be true about the size of the subgroup relative to the size of the original? This is a good place to stop. We will continue on Thursday. copy Pythagorean squared A